I know you would have.
All right, so today, I had a question sent to me, are we supposed to do the MATLAB problems or MATLAB components? You're absolutely allowed to do them. I'm not gonna collect them, so you don't have to do them. But MATLAB is one of those things, it's a tool. Have you all used MATLAB in here before? Yeah. MATLAB has a lot of features that are really nice, and I might say this. When you go out in the real world, you're going to find out that most of the prototyping codes, the first codes that are developed, are either written in Python, Octave, or MATLAB before they ever develop the really fast codes, taking C and stuff like that, and C++, where they just literally take MATLAB code as a translation, I call it a translator. They take that code and turn it into a C code, if you want. And that's the real efficient ones where you can compile and get them. One other thing about in Dr. Whitmer's book, he has things where he has root-solving routines that he creates using Newton-Raphson and stuff like this. MATLAB has all that built in. It's called solve. You know how to use MATLAB's solve function? All right, you do. It's you simply put in the equation you want to solve, literally. Have it a double equal sign. Say it's, I don't know, x squared minus 2x minus 1 equals 0. It'd be x squared minus 2x minus 1, 2 equal signs, 0, comma, x. You put the word solve in front of it, and it'll give you solutions, all of them. It's the same way with, you're doing those, remember the power patterns for the arbitrarily long dipole? You can get a maximum value of that angular function that's much greater than 1. Well, if you want to find out where it's a maximum or where it's a minimum, you can do that too with MATLAB in a heartbeat, and it's very easy to do. So I'm just telling you, MATLAB is available to you, but I'm not going to require you to write any MATLAB code or quizzes or tests, just so everybody knows. I do expect you, when we get to the project, MATLAB will be a component of it. You're going to have to use MATLAB to do this. So, who asked me about that? Somebody said, you did? All right, I hope I'm clear about that with you. And I even think I sent you the solve code.
You did.
All right.
I was just wondering if those particular problems, if you assigned them, if you want us to do them by hand.
Well,
overtime.
it's just, honestly, for the halfway dipole, you can do that. I mean, I'm just going to talk about this one thing, because being with something I didn't spend a lot of time with, but I want to mention is being with, half-power beamwidth is real important. So I'm going to talk about two aspects of this, and I'll tell you what I mean by how you can solve this without using MATLAB, but MATLAB will make it real easy. So if you take a short dipole, just a short dipole, you know that the electric field as a function of angle is simply j beta I L over 4 pi r times e to the minus j beta r times the sine of theta in the a theta direction. You know this, right? If I go ahead and I square this thing, I can say that the average power from this, the average power matter, the power density is 1/2 magnitude of e squared over eta in the AR direction. You can get that too. You're going to find out it's going to have to do with some constant right here times the sine squared of theta. Does everybody follow me on this? I'm not even going to bother figuring out that constant. It has to do with eta, beta, I, all that stuff. But it's a simple constant. It doesn't change. Y'all follow me? And yeah, it is a function of r squared, but we don't care about that as much as we do how it varies with angle. Y'all follow me? Now, if you look at this and you were to plot this in a polar plot, it would look like this. You would have a maximum value out here of simply k, whatever that constant is, and there would be 2 points in this plot, and from here down, where you would have a value that is going to be 1/2 that value, 1/2 k. So it'd be right here, it'd be 1/2 k. It's half the peak power density. Y'all follow me? The beam width itself is this. it's called a 3 dB beam width, or half power beam width. I think what book calls it half power beam width. The way you figure it out is, if you look at the angular function here, you know the sine squared's value, the maximum value is 1, that's at 90 degrees. Y'all follow me there? So if you want to figure out where the half power beam, where this point is or that point, you would just take the sine squared of theta and set it equal to 1/2. For that one, that sine of theta is 1 over square root 2, that's 45 degrees. So here, theta would be either 45 degrees or 135 degrees. They give you the same value. Y'all follow me? Now, the beam width, I mean, if this is at 45 here, and this is at 135 right here, the beam width itself is this, or it's simply this angle minus that angle, or 90 degrees. Do y'all follow me? That's the beam width, half power beam width. If you have something with a more complicated function, and this is what you asked me about, so if you have something where you have, like, let's do the halfway dipole. For the halfway dipole, so this is a lambda over 2 in length dipole here. Now we find that the power density, the average power, is going to be equal to some constant k, and then it's going to be times cosine of pi over 2 cosine of theta over the sine of theta squared. Y'all follow me? Now that angular function, this right here, in Whitmer's book, he has this labeled as f of theta, capital F. How many of you realize that from his book? If you haven't read it, just be aware of this. He uses a capital F of theta to indicate the angular variation in the power pattern. Now, for this one, this does have a peak value of 1. But if it was the arbitrarily long dipole where you had the cosine of beta L over 2 coming off that, then you don't know. It gets much larger than 1. Then you have to evaluate where that angular function is a maximum and know the maximum value. And you have to divide that in to the angular function to get a normalized value. You all follow me? All right. So back to this. If I ask for the half power point on this one, right? Well, its peak value, I'm just going to tell you, that function has a peak value of 1. It's just like sine. So you know it's at 90 degrees. You all follow me? This will have a peak value at 90 degrees. And it will be 1. So to get the actual beam width using this function for halfway, you would set cosine of pi over 2 cosine of theta over the sine of theta. Now you should square this and set it equal to 1/2. Alright? But what I'm going to do is say, I'll just make this equal to 1 over square root of 2. Because that's the same thing as squaring it and set it equal to 1/2. It negates the squaring factor. Y'all follow me? Now, to get this, there's a couple different ways to do it. One way is, you go ahead and you solve for it. You take a guess at theta, solve for it, and see how close it is to that. Take another guess and basically iterate back and forth and just get close. Y'all follow me? And there's an Rafson routine he talks about, there's different things. The easiest way to do it is with a solver like MATLAB or MathCAD or Mathematica, where you just literally put this equation in, right, and solve it. I'll just point this out to you. You asked about it, and it's a good one. So if you have MATLAB, it would be, I think it's SOLVE, but you need a symbolic toolbox. Do this. So you solve, and then you would have the function right here, which is going to be cosine pi over 2, cosine, and call it an x, over the sine of x. It would be that, and you could have it equal to 1 over square root of 2, comma, and then just, it has to be a double equal sign, comma x, and it'll give you a value, it'll be in radians. Has anybody ever tried that, this solve function? Did you try it after I sent it to you? Did you notice, you have to use symbolic, I think, right? Didn't it say SYMS? So I had to download that. But you can do this in Octave too. Octave is free MATLAB, basically, it's a little slower. There's Mathematica, I use MathCAD for this kind of stuff. But there's solvers all over. I even think that, what's that Wolfram Alpha thing? It's online. I think that does that too, even though I haven't checked. So just remember, and then what you would do, when you get this, you're gonna find two angles. You get one that'll be about 45 degrees, and another that'll be about 135. A little more. Here it'll be about 47 to 48 degrees. Here it'll be about 132, 133. Then that would be the beamline. You follow me on that, class? And that's how you get the half-power beamline for any of these things. I hope I'm clear about this. I just wanted to cover it, I wanted to answer your question. I had other people ask me similar questions, but not quite that direct. All right, now, about the homework. Anybody have any questions about the homework besides the MATLAB component of it? Or any problems they want to see with it? Because I gave you covered phrase, right? And I gave you, I don't know how many problems related to that. I almost want to do one of them, but do you have one for me? Michael, did you have a test or something?
Yeah,
You did?
we have it.
Oh, you have one. What course?
Communication.
Communication. No, it's right there. No, he's good. All right. He's predictable. I think. I hope. For your sake. All right. So that explains part of the reason this is so quiet. Do you have a problem? Did you try any of these or not? Nothing? I think we should do at least one. Go ahead. You pick.
Can you use 7.2.2?
Yeah, can you tell me?
There's a lossless quarter wave monopole antenna.
Oh, there's a monopole antenna.
Over perfectly conducting length, driven by a 100 volt, 300 megahertz source.
100 volt. F equals 300 megahertz.
So the source impedance is 50.
Okay, 50 ohms. This looks familiar.
Determine the total average power radiated.
Wait a second. Did you do this one?
Never mind.
Never mind. All right, and what, is this an exact half wave?
A lossless quarter wave.
Oh, quarter wave monopole? Okay. So it's Lambda for monopole. They want the power radiated?
Yep.
Okay. He basically doesn't have any transmission line connecting, so we don't have that problem. This is direct connection. So first is, if that's a quarter wave monopole, you know that the Z antenna, if it's an exact quarter wave monopole, it's going to be 73.2 plus J 42.5, right? All over 2. You all follow? Because it's a monopole, it's half the antenna impedance of a dipole. Everybody follow? Because half the power is radiated. Now, with that in mind, we can see, what is this exactly? So that's 36.6, right? Plus J 21.25 ohms. That's your antenna impedance. So what we're going to do now, electrically, this circuit will look like plus or minus 100 volts, right? Then you're going to have a source impedance here of 50 ohms. And then you're going to have your antenna impedance of 36, this would be the antenna, 36.6 plus J 21.25 ohms here. And the big thing we need is this current, right? So that current's really going to be, and that's a peak current, by the way. The peak current here is going to be 100 over, and that's going to be what? 86.6 plus J 21.25. So if you can give me just the magnitude, I don't care about the phase, just the magnitude of that current anyway. I'm teaching a class in EMC, it's electromagnetic compatibility, and I'm teaching this course. We're doing the exact same thing we're doing for this. So I'm not sure where you can give me magnitude and angle if you want to.
1.121.
1.121 at some angle, right?
Negative 13.8.
Minus 13.8 degrees. That doesn't matter, right? Now, they asked for the total power radiated, is that right?
Yes.
All right, think about it. Just think about this. If I have the current, how do I get the total power radiated? It's very simple. What is the total power radiated going to be? What is power in general? If you just had a resistor and you knew a current, hint. So what? 1/2 magnitude of the current, right, squared times the resistance. In our case, it's the radiation resistance. Y'all follow me? What is the radiation resistance for this one?
36.6.
That's right. It is the real part of the antenna impedance. It's 36.6 ohms, right? So this is going to be 1/2 times whatever that is, 1.121 squared times 36.6, and that should be how much power is radiated. Can you tell me what that is?
23 watts.
Is it 23 watts? Is that the answer?
The answer is 23.
Y'all follow me? Now there's no transmission line in this one, right? It's a direct connection. If there was a transmission line, then it gets more complicated. Then you have to figure out how much actual current would be at the load once the transmission line's effects are integrated into it. That's a much longer problem, by the way. Everybody got that? Okay. You got another one? Is there another part to that problem?
Down at 7.2.3 says that the problem is the same, but it's now a 1/5
Okay.
The rest of, 7.2.2 has the magnitude of the electric field.
All right. Why don't we just finish that one? How do we get the magnitude of the electric?
And the power density.
At what range?
Distance of 100.
At 90 degrees?
Yeah.
All right. So if this is a quarter wave monopole, and we're exactly at 90 degrees, it's right on the ground. Here's what the dipole looks like, right? We would be out here, did you say 100 meters? Yes. 100 meters away, they want the power density, PAV, right? And they want the electric field. Now, this is up to you how you get it. I usually just go for the power density, but you can get the we can do the electric field one using the electric field equation that's given. We know that the electric field for a dipole, and it matters not if it's a monopole or half-wave dipole. Once you know the current, this equation is the same. The electric field, if it's a half-wave, would be simply J times 60I over R. Then there's that e to the minus j beta r, which is a phase term we can forget about. And then there's the angular function, cosine pi over 2 cosine of theta, all over the sine of theta. And it would be in the a theta direction. Now this is in the far field. But I want to tell you, at 90 degrees, that function is 1. That's the nice thing. Got it? You don't have to worry about it being some weird number. It's 1. You don't have to calculate that. Therefore, the magnitude of the field is just equal to 60 times I over R. And that's going to be 60 times, what is it, 1.121 divided by R of 100, and that should be, this is one way to get it. What's the electric field? Do it this way. I'm just using the electric field equation for half-wave dipole, which is the same as a quarter wave monopole. Y'all follow me? It's only dependent on the current. So what is this value? About 0.6 something, 0.68, what?
Yeah, 0.674.
0.674 volts per meter. Is that the right answer? Is that right? For the answer, 0.674?
Yes.
All right, how else could we do it? This is the way I usually do it. Well, I would get the power density, right? How do I get the power density? The way I always get, if I want the average power density, what's the trick? I always take total radiated power, right? Total divided by, that's right, 4 pi r squared. Now that's the average power density. Then you have to multiply by the gain, right? Now in our case, it's a monopole. So the directivity or the gain is 2 times the value of the actual dipole. Do y'all hear me on that? The dipole antenna had a peak gain of 1.64, right? The half-wave dipole. This will have a gain of twice that. So it's going to be 2 times 1.64. And there will be a maximum there because it's at 90 degrees. So if we do this, we'll get the average power density this way, then we'll get the electric field. So it's the radiated power, what was that again, 23 watts? 23, right? And then we're gonna divide that by 4 pi r squared, and r is 100 squared. And then you have to multiply 2 times 1.64, so this would be the power density in watts per meter squared. Y'all follow me on what I'm doing? Did you have a question? Okay. Everybody? So what is that? If you don't mind helping me. 0.6. Is that confirmed? 0.6? Just check. Is that right? Alright, 0.6 watts per meter squared. From that, how do I get the electric field? Remember when first. What? Milliwatts, sorry. That sounds better. 0.6 milliwatts per meter squared. So how do I get the electric field once I have that? What do I always think of? In free space, isn't the average power density always equal to 1/2 times the magnitude of the E field squared over eta in free space, eta naught? So that means the E field would be what? It would be the square root of 2 eta naught, or 120 pi, times Pm, right? In free space? That's equal to the square root of 2 times 120 pi times 0.6 times 10 to the minus 3. What do you get? You're going to get 0.674 volts, aren't you? Now, I usually use the total power radiated by 4 pi r squared times the gain, or directivity, to get the power density, then I derive the E field or H field. Usually that's quicker. For this one, you can go either way. If you want the E field, you can get that. And by the way, if you took that E field and went back and got the power density, it'd be the same. But that covers all bases of that question, right? So, all right, why don't we do the next one, because you asked about it. I think it at least should give everybody a good feel that they understand this once we do it. So for the next problem, it says only one thing different, right? It says it's a lambda over 5 dipole, but it gives us what?
Gives us the input impedance 20 minus J50.
Which is really nice. So now, here's my equivalent circuit for that. Same source voltage, plus or minus 100 volts. F is equal to 300 megahertz. Have RS equal to 50, right? And then I have, is 20 minus J, what is it?
J50.
20 minus J50. So then I have 20 minus J50. Now pay attention to this. So now I'm given the antenna impedance, that's Z antenna. So what's my current going to be? 100, right? Over, what is it? 70 minus J50. Can you just give me the magnitude of that? We don't even need the phase. Y'all follow me on how to do this? I mean,
But we don't add the 50 for the quarter wave?
well, look, here's what I did. See, the 20 and 50 is 70, right? He's replacing that quarter wave monopole with this lambda over 5 monopole, isn't that right?
I was just wondering, since on a quarter wave, we divided by 36.
No, we took the half wave impedance and divided it by 2. Right? The half wave, this is given, the impedance of the monopole is given. It says directly, this is it, use it. He says it's 20 minus J50, right? Alright, that's it. You don't have to do anything else with that. That's a monopole. So what is this current? 1.162 amps. Alright, now forget about the angle. You don't need it. Alright, think everybody just for a second. Force yourself to ask, how do I get the power radiated now that I have the current? It's always going to be what? 1/2 times I squared times the radiation resistance. What's the radiation resistance? Just looking at this. It's 20. Y'all follow me? It's the real part of the antenna impedance. That's the radiation resistance. So then you can figure out the power radiated. We'll make sure this is right. It's going to be 1/2 magnitude of 1.162 squared times the radiation resistance, which is 20. So it's really 10 times 1.162 squared. Anybody? 13.5, you say? Is that right? Is that the answer? All right, does he ask anything else in that one? If you go through, you can knock these problems out one by one very quickly if you understand this. That's the only thing you have to get is the current and know what the radiation resistance is, and you can get power rating. If you know the directivity, you can get the actual electric field, or really power density or the electric field easily, and it's always the same. Now for the freeze problems, those problems are just dipole, but for the freeze problems, did anybody try any of them? You did? I'd like to do just one of them because freeze transmission is something that you're going to get a quiz on. Now you wake up. Did you say quiz? I mean, you have to know this to do freeze, in a sense, all right? But freeze is, it's going to be how much power is received by the second antenna, and then you have to figure out, when I change the load, what the actual voltage would be on a non-ideal load. You all follow me? So please hear me on this one. By the way, that storm looks like it's going to miss us, right? I mean, it's making landfall right now, and I was told that they always, I don't know, somebody draws a short straw and they got a reporter up there hanging on to something for dear life while the wind's blowing them away. But anyway, I think it's going to cut across Florida and then get into the Atlantic and come up and hit somewhere around South Carolina, I think. So I don't know how many people here went down to help family, but I think a few have, just from the information. Okay, so now for freeze, you got one in mind? You want me? Fine. I got one in mind. This is, you got a test in communication. How many have that test? Well, good luck. He is predictable, though. Don't tell him I said it. I mean, I don't know about, I'm not going to say anything about professor now. There's some professors I had extremely hard to figure out what they're going to ask. They can ask you for a proof. They can ask you for actual values. One of those things that drive you nuts because you didn't know. I don't know if he's going to ask me to prove Bessel function solve this equation or something crazy like that, or if he's actually going to ask me the solution for an electric field from a given current density. But all right, so how about problem 848? And here we have two different dipoles. This is problem 848. Just work with me on this one. He's got a dipole here, and I think it's 3 meters. You tell me if I'm wrong here. And then he's got some distance on. He's got another dipole, and this is, I think, 4 centimeters. Am I right on this one? This is on page 497. It's 4 kilometers away. So here R is 4 kilometers. And what else does he have on this problem? Then he has a 50 megahertz source. So he's got F equals 50 megahertz. And the only thing he wants is the ratio of power received to power transmitted. He's not even worried about the total power density or the power received. He's looking just for that ratio in this problem. Okay, I'm gonna add a few things to it. So to get that ratio, P received over P transmitted, that's equal to lambda over 4 pi r, right? It's going to be that squared times gain of antenna 1 times gain of antenna 2. You all agree that that's freeze, at least in a nutshell, right? We proved that. So we have to get the wavelength. Alright, what's the wavelength gonna be? It's C over F. I hope I'm right, it's 50 megahertz, right, class? Isn't that a problem? Alright, if it's 50 megahertz, this is what? 3 times 10 to the 8 over 5 times 10 to the 7th, right? 50 megahertz is what, that's down 7. So what is that? That's 30 over 5, right, or 6 meters. Do you agree with that? If it's 6 meters, this would be what? This is exactly lambda over 2 length dipole, isn't it? Y'all follow me? You have a question?
What is the R value beside the R?
This is 4 kilometers.
Okay.
This is the problem. It's 4 kilometers is the actual range. The second antenna. They're both.
What's the height of that one?
It won't matter. This is, oh, I'm sorry, this is 60 degrees. Okay. You've got, the height won't matter. Or the length, you mean?
Yeah, going to the.
4 centimeters. If you check, tell me if I'm wrong on that one, I believe it's 4 centimeters. Now, so the first antenna is a half-wave dipole. Do we all agree on that? The second antenna is what? Well, if 6 meters is a wavelength, that's a whole lot less than a tenth of a wavelength, right? Y'all follow me? So that's a short dipole, right? So you can just put this as a short dipole. Okay, now coming over to this equation, because we want the ratio, I got lambda, which is 6, over 4 pi. Then I got R, which is 4 kilometers, so it's times 4,000. I have to square that ratio. Then I need gain of the first antenna. Now this is an ideal, it's a half-wave dipole, so the gain is going to be 1.64. Then you have to put the angular function. So it's going to be cosine of pi over 2, cosine, and this is 60 degrees, right? That's the angle. It's measured from the vertical axis of the antenna. 60 degrees. Then it's over the sine of 60 degrees. And that has to be squared. So that takes care of the gain of the first, or really, I call it the gain. The efficiency is 100% in this unless they specify something else. Then I have to get the gain of the short dipole. What's the peak gain of the short dipole, anyone? 1.5 or 3/2, right? So then you're going to take this, and you're going to take 1.5, and then the normalized power is going to be sine squared of theta, or really sine squared of 60 degrees. And the reason I know that is because these two are vertically pointed, and this angle here would have to be 60 degrees as well. Because alternate interior angles have the same angle. Y'all follow me on that? So now, if you look at this, we can probably make some adjustments here. So what is the sine of 60 degrees? Sine. Isn't it 1/2? I mean, you don't have to do it. If it's 1/2, you square it, you get 1/4, don't you, class? So I have 1/4 times 3/2, right? So that's going to be 3/8. Then you're going to have to calculate that right there and square it. Go ahead, when you do the calculation, what do you get for this? Because this is the ratio, if you don't mind.
The cosine of pi, when we have for the half-wave dipole, when
This would be in radians.
that
The
needs to be in radians.
Yeah, the cosine is 60 is what? Isn't that? I'm sorry.
Oh, cosine is 1/2, sine is 60.
I'm sorry, I said it wrong. The sine is 60. I was wrong on that. Sorry about that. That would be 1/2, so this would be cosine of pi over 4. So that's going to be square root 1 over square root of 2. I don't know, what does this come down? I'm sorry about that. Since I've had COVID, my face still isn't back 100%, and I got nagging little pains that haven't completely gone away. But I saw my doctor yesterday, and he told me it took him 5 weeks to get over the long-term symptoms of for him. How big is that guy? That's almost one, go ahead. What do you keep it for the whole thing? Anyone?
17.5 nanowatts.
Anybody else? What'd you get? What'd you get?
I don't know what I put this in, but I thought I got 29.4.
29.4. Anybody else?
That's 17.
I didn't.
17?
I got 17.
17 nanowatts? 17 point something nanowatts?
Is there?
Point what?
I found my answer.
Just 17 nanowatts?
17.5.
0.5 nanowatts. Really? Not nanowatts.
Nanowatts.
No, it's just ratio, so it's just 17.5 times 10 to the minus 9. It's power ratio. Is that the right answer? Can anybody tell me?
Yes.
It is? Good. But that's how you do that. Now, if I actually gave you the amount of power transmitted, you could calculate the amount of power received. Y'all follow me? Then you would have to get the open circuit voltage, remember that, in order to complete the problem. I just want to mention this. So, for this problem, if we had a certain power transmitted, you have the ratio, then we could get the power received, right? But in order to complete the problem, if I attach any kind of a load to that antenna, the second antenna, then you need to find the equivalent circuit here, the plus or minus VOC. Then you have the antenna impedance, it's exact half wave, or sorry, this is a short dipole, isn't it? Yeah, that's a short dipole. So for this one, it's just gonna have an R ras here that's going to be equal to 80 pi squared L over lambda squared ohms. But there will be a reactance too, and I'd have to give you that. It's minus J something. And I'm not even going to bother putting it in here for this one. Then you would put the load on, so whatever my load would be. But this V open circuit is the key thing. If you remember me going through it, that was equal to the square root of 4 times P received times the radiation resistance of the antenna. Y'all remember that? Now, the reason I'm putting it on here is because you guys are going to see this on Friday, so I'm just making sure that it's clear as a bell what you're expected to know. Got it? All right. Now, the next thing, and the last thing I'm doing today is going to be radar. We'll do the actual array theory on Friday. But so now I'm going to go through radar. Unless there's another question about this. Radar is, and it's a very simple approach to radar these days. So, I teach a course in radar, and I'm doing some research in radar. But the big thing about it is that you have to understand with radar is that really you're dealing with the same thing sonar is, only you're using electromagnetic waves instead of sound waves. It's the same exact principle. Now I gotta tell you one other thing about radar in general that you don't understand and you don't appreciate yet. Alright. If you look around you, you can tell how far you are from like that alert back there, that box, from that thing, from that. You can take a look and you can see everything. You're not transmitting it. You're using the ambient sources of electromagnetic energy in the room as the sources that cause a reflection in your eyes and your brain. The neural network of your brain figures out what's there. And it's amazing how the level of detail you can see. You're not transmitting anything. That would be called a passive radar. If you actually had a system that didn't transmit anything, that used the ambient energy in the background in the microwave range to actually figure out what's there. There are passive radars. But passive radars can't do anything near what your eye can do, your brain and your eyes. Because your brain is a neural net that's so many orders of magnitude better than the best neural nets we can make, the artificial intelligence. You can't teach them fast enough how to figure out what's going on based on reflected electromagnetic energy. But that's exactly what you've been looking at. You're looking at photons, you're figuring out everything. Without even thinking about it, it's automatic because you've been taught since you're young. Now, with standard radar, we have to create a signal. That's what bats do in terms of sonar, that's what dolphins do. They generate a signal, and then they listen for the echoes back. That's really what it is with radar. It's really radio detection and ranging systems. That's all it is. So we generate an electromagnetic signature, we launch it, and then we listen for an echo return. And from there we can figure out distance because we know how fast it's traveling. We can figure out a lot of things, and there's two kinds. There's monostatic and there's bistatic. The most common is monostatic. It means it uses the same antenna to transmit and receive electromagnetic energy. So, when we talk about radar, and this is going to be monostatic only, we're going to have a system that's going to transmit a certain amount of power. This antenna is going to have a certain amount of gain. I'll just use G, it's the gain of that antenna. If I come out a distance far away, I would have a power density out here, an average power density, equal to the transmitted power over 4 pi r squared times the gain of that antenna, called gain 1. Y'all follow me? That would be the power density. Now, if a target is out there at a range r, the target has a radar cross section. A radar cross section, RCS. The symbol Dr. Wentworth's book uses, and most books use for radar cross section, is sigma. I know we use that also for conductivity, but it would be very obvious if this would be a radar cross section because the units are meters squared. Right? So that's how big it is electrically. Now, when this signal hits this, it's going to re-radiate power. And the re-radiated power density, I'll just take you through this. I come at it and I have an average power density, P-ab, right? That's right here. Then it's times sigma. That's the total amount of power re-radiated. Y'all follow me? It's basically, that sigma value is like the aperture in terms of the size of the antenna. It's in meters squared. This is how much power is going to be re-radiated. Now, as it re-radiates, it falls off as 4 pi r squared as well. So this falls off as 4 pi r squared. And now that power density is what's back here. Y'all follow the progression of this. I launch a wave, I have a certain total transmitted power, now I get the power density on this target. That power density hits the target. You might say the target catches a certain amount of it and re-radiates that power. All that re-radiated power falls off as 1 over 4 pi r squared. Now that power density is coming back here. And when it collides with this antenna has a certain electrical size called the aperture, and that's how much power is received. So when I take this right here, and I'll clean this up for you in a second, I multiply it by the aperture, which is lambda squared over 4 pi, then it will be the gain of this antenna, the first antenna. That's the electrical size, and this would be P received. I'm going to go ahead and put in all the terms of this. And what you're expected to know with a radar problem, have to know how much power density is on the target, have to know how much power is radiated back or scattered by this object, the target, and then you have to know the power density back of this antenna, and then you have to figure out the amount of power received by that antenna. That's that equation. Now when you look at this, that means P received here, back at the antenna. Well, that P average is really P transmitted over 4 pi r squared times gain of antenna 1, then it's times sigma, and you have another 1 over 4 pi r squared there. Then you have lambda squared, then you have gain of antenna 2, and then you have another 4 pi. So that's what happened. When they neatly condense things, they get this. They find out that you get a ratio of P received over P transmitted. This is similar to Friese. Is going to be equal to gain of the first antenna and gain of the second antenna, but they're one and the same in this case. But I can put gain of the first, gain of the second, then it's times sigma times, and then what they normally do is put lambda squared. They divide this by 4 pi cubed, and then by r to the 4th. And that's what he'll have in his book. He may use directivities instead of gains, but usually gain of, if it's a monostatic radar, the gain of the antenna is the same because they're using the same antenna. Gain 1 is gain 2. If they have 2 separate antennas, then it would be different. But generally speaking, they're the same. And that really is, it's called a radar range equation. That's the first thing you have to know about radar. The second thing, does that make sense to everybody? And these are just straightforward plug and chug kind of things. Obviously, you can get things where, and I'm not going to spend too much time on this, the RCS of the object is a function of the angle of incidence of this. For instance, if you have an aircraft or just a missile, a long missile, you look at it this way physically, it's small, looks like a dot coming at you. If you look at it this way, it's much larger in terms of its cross-sectional area. And for the most part, the electrical size of an object to an antenna, if it's many wavelengths across, is about the physical size that your eye sees. So if you have something that's got a cross-section of 1 meter squared and a wavelength like a centimeter, electrically it's about 1 meter squared in terms of its actual electrical size, assuming it's a conductor. And we're assuming these targets are fairly good conductors, though they don't have to be. So the next thing we're going to talk about is Doppler. How many know that term Doppler? You should from physics. It has to do with something where the actual frequency is altered by the movement of an object. And if you've ever been to a race and you hear cars coming at you, you'll hear the engine just go up, and when they pass, it's because not that the actual RPMs of the engine change, but that the velocity the car is going in either compresses or you might say extends, or really, yeah, it would be extending the wavelength if it's going, if it goes past you, because it's a sound at a lower frequency. So here's how we figure out Doppler in a simple sense. If you have a radar here, and I'm distance r away, and I have a target, but the target has a velocity component in the direction of the radar. Y'all follow? Alright. This is the way he does it in his book. I could do it with a relativistic formulation too, but it's a little more complicated and doesn't really buy you anything, because all the radars you're going to be exposed to, at least in the near term, are going to be terrestrial radars where we don't have to worry about speed of light effects. But if you take a look at the total path that that the signal goes through the radar, it comes out, hits here, and back. So it actually goes over a range of 2r. Y'all follow me on that? That's the total distance, path distance. By the way, how long did that take? If I knew what r was, how long would it take anybody? What limits that speed? Speed of light, right? So you would say c times t would be 2r, right? Therefore, t would be 2r over c. That would be the delay time from the time you launch to the time you receive. That delay time can be used to estimate range, and it is. If I take this, though, and I divide by wavelengths, now I have the number of wavelengths that the actual wave, or that the electromagnetic energy went through. Y'all follow me? Then if I take the number of wavelengths and I multiply it by 2 pi, now I have the total number of radians that are changing. Right? The wave would have gone through that many, you might say, radian distances, the radians per meter times that. And that would be something that we just call the angle. Now, when you take the time derivative of this, that's going to be equal to 4 pi over lambda times dr dt. Well, that time derivative right there is really omega Doppler, and that's 2 pi times f Doppler. I don't know how they showed you this in physics. Now that Doppler frequency is gonna be the shift in the actual electromagnetics high frequency signature. So if it was sending at a gigahertz, if this thing's coming at you, it's gonna come back at a frequency slightly higher than a gigahertz. If it's moving away from you, slightly lower. So this is what you wanna know. And that means the Doppler frequency shift, and it's not much. If you take a look at this, I have 2 pi, 4 pi, so it's really gonna be 2 over lambda. And the RDT is really the velocity, and this is the Doppler frequency shift. If something's coming at you, the Doppler frequency shifts the actual transmitting frequency upwards a slight amount. If it's going away, it shifts it down a slight amount. Does this make sense to everybody? When you taught, this is how they taught it with, in physics when you got Doppler shift or not? Alright, they should have done it this way. They can do it with doing the relativistic way, but that's a little more involved and it's not really useful for practical things that you're gonna be exposed to. That's the Doppler frequency. So if you sent a waveform and it was at a certain frequency, when it returns, it's gonna be shifted up or down by that amount. We're gonna pick that up on Friday and talk more about that, but I'm out of time. I hope this made sense to you today. I wanna make sure I get at least a few problems.